for today's webinar. Before we begin, I would like you to let you know, inform you of the upcoming events. As you can see from this background slides, that we have our World Congress coming up in December. And you can sign up for it. The program is listed on the IDRA websites, and we hope to see you there. So this webinar is called Maven Brine Mining, and it's the first commercial osmotic-assisted OARO project in the world. The webinar, it contains information on the design, so the design, the implementation, and the operational outcome of this project. And this plant is located in Indonesia. So some statistics about this plant is that it produces 220,000 tons of salt per year, and it produces 25,500 cubic meters per day of desalinated water. So this webinar, during this webinar, we'll be exploring topics such as advanced design and engineering strategies, innovative brine mining solutions, operational key parameters, cutting-edge technologies in high-pressure pump and energy recovery devices, the role of osmotic-assisted OARO membranes in improving efficiency and reducing energy consumption. To learn how this groundbreaking plant is redefining brine mining markets and advancing industrial sustainability. Now I would like to introduce you the first speaker, and the first speaker is going to be Mr. Ersan Ozdemir. Mr. Ozdemir is the head of engineering at Hyrec. He has a degree in environmental engineering and has more than 14 years experience in wastewater treatment and water desalination. The last 6 years he has spent on membrane and process development on seawater mining and brine concentration applications at Hyrec. He has been very involved in this brine mining project with brine concentration membrane processes. Please proceed, Mr. Ozdemir.
Thank you very much. Great. And good morning, good afternoon, and good evening to everyone. My name is Ersan, and I am excited to be here today. First, I would like to thank IDRI and Danfoss to organize this webinar. I am thrilled to participate in this webinar. Quickly introduce myself. I am Ersan Ozdemir and specialized in desalination and brine mining process and membrane development. I have been looking forward to today discussing what kind of difficulties did we encounter and during to build the first large commercial ocean mining project. And it was really an interesting journey and still ongoing. And we will try to explain our experiences and our enjoyment during this journey. We can start, and yes, the project in Indonesia, and the name is Maven Desalination and Salt Production Plant. We are actually, the main product is salt at that plant, and water is byproduct. We are not focusing to water production. The customer needs the 220 ton per year as a food grade salt, and we are producing this amount of salt from the plant, and we are also selling the desalinated water to the neighborhoods around the plant. And the client is PT Annual Hayat Sejahtera, and this salt is using for food grades application and for noodle, actually biggest producer of the noodle in Indonesia, and located in northwest coast Indonesia and Java Island. And purposes of this reduced amount of salt imported from abroad. This is interesting market in Indonesia because they have limited natural source in the islands, several islands. So that's why they are importing to 85% of the salt from Australia and China and India, and just 20% of the salt they are producing from solar farmer. And if you consider they have very huge rain season, which is monsoon season, they have intermittent process and production. and the limited sources, and the market, actually the production is not available 100% of the time. So the timeline of the project, we started 2018 at this project with feasibility study and basic engineering and process design. And at 2019, we started the basic engineering design, and with process design completed and process block diagram completed and all financial diagram completed by us. And we started 2020 and a bit evaluation, and we collect a lot of inquiries from the market, from Europe, from Asia, and from America as well. And we evaluated those bids at that stage. Then we started 2021. We started the FEED, front-end engineering design, in 2021. And of course, COVID-19 impacted our timeline, and it's extended a little bit because we couldn't travel and we couldn't communicate very well with the parties. So that's why it's a little bit extended. And finally, we started 2021 and 2022, and project execution started on site. And we also provide as an owner engineering to the customer and to our customer, and manufacturing supply of package. And we commissioned the plant 2023. And we produced first salt, as far as I remember, September or October at 2023. And during this time, until that time, sorry, we are producing salt and water, and we are also supporting our customer with as a OEM support, operational maintenance, and we are responsible to good quality of the salt and operation of the membrane section. Next slide, please. And what was our design strategies? That was very interesting, because the market was willing to and focused to produce only water from the sea or any kind of sources in the world. But if you focus to produce mineral or salt from the sea, that was the biggest challenge, because membranes are different experiments, needs different knowledge and engineering practice, and evaporation side needs to completely different engineering practices. We combined these two sections, and we were a bridge in between membrane section and evaporation section. And the main goal of this strategy is the energy consumption, energy efficiency, and high purity brine saturation limit with thermal system, capital and operational cost, and easy operation. Technically, to produce the salt is available on the market and in the world. If you put the salt evaporator or the seawater, you will able to see the salt, even high quality salt. But the problem is time and operation and capital cost. Even today, we can directly get the OARO concentrated brine and feed the evaporation, and we can produce food grade salt as well. But in this case, the capital and operational cost is not getting feasible. And that's why the Hyrec brine concentration process is getting a bridge in between seawater OARO and evaporation, and helping to the project finance. I will try to explain a little bit in the next slides. Can we go next slide, please? Yes, this is the typical and basic explanation of our goals of this project. Without brine concentration membrane system, evaporator will be 4 times bigger. If we consider temperature, which is 120 degrees Celsius, and concentration, which is around 250,000 milligram per liter, and its corrosive behaviors of the sodium chloride solution, that is extremely too expensive processes and equipments. You have to go the exotic metals, Monel, Hastelloy, or Alloy 31, and that is extremely too expensive in the market. And also, if you can see on the graph, on the bottom line, total dissolved solids. On the other line, specific power consumption, kilowatt hour by cubic meter desalinated water. It's very critical, by the way, because we are hearing lots of specific power consumption to based on to some feed water, to concentrated brine, or to others, which is not correct. That has to be divided into the desalinated or condensated water. So those power consumption is kilowatt hour divided desalinated water. And we consider here without brine concentration membrane section and with brine concentration membrane section. As you can see, the capacities of the evaporator getting a quarter and operational cost getting half. So that's helping to the project finance in terms of capital costs and also operational costs. Next slide, please. This is process flow diagram of our plant. Respectively, the plant is consisting of UF, NF, seawater RO, osmotically assisted RO, and falling film evaporator and crystallizer. The plant is consisting 3 identical train entirely of the membrane section. All of us is well known on the UF aim is to eliminate organic matters and total suspended solids. Why actually we are getting lots of questions on that, why we haven't used multimedia filter. I never seen 82% recovery the reverse osmosis plants. If you consider 82% water recovery, the silk density index is getting very important on the feed of NF. Therefore, we have to reduce silk density index less than 2.5 as a STI 15. Then the plant and membrane system will be much more safe. So, of course, the nanofiltration system is heart of this plant because the aim of these membranes to eliminate multivalent ions. During the eliminating and rejecting multivalent ions, the membrane should be not eliminate monovalent ions, which is sodium chloride. What I mean by that, we need to pure sodium chloride solution, and also we don't want to dilute NF permeate stream. And that's why this is specific membrane and heart of the plants, because it will help to operational availability of falling film evaporator as well as crystallizer. And also, if you consider those plants as very expensive and their operational cost quite high, the plant availability is very critical position of those 2 elements, two equipments. If, of course, those plants can run under the high calcium and magnesium condition, but plant availability will be less because we have to stop the plants and perform cleaning, chemical cleaning into the heat exchanger and the circulation loop as well as falling film evaporator. That's getting the time, and it's not helping to us increase operational availability of these 2 plants. After that NF, we have seawater RO, regular seawater RO, but it is running very high under the very high pressure, operating pressure, and under the high recovery, which is 58-59%. And after the RO, we have osmotically assisted reverse osmosis. We are able to concentrate 16%, which is almost 180,000 milligram per liter. And we do have diluted brine, which is coming back to the field of seawater RO. After that, osmotically assisted RO, we are feeding this brine into the falling film evaporation, and after that falling film evaporation, saturated brine is feeding into the crystallizer to produce food grade salts. We are getting mostly why we are stopping 16%. This is depend of the market situation, and actually there is always breaking point in terms of operational and capital cost. 16%, especially for Indonesian market, because energy is cheap. And water price is also very cheap. That's why if we consider these 2 low cost, we have to stop 16% weight to weight in terms of economical feasibility. And you can see also here the red one is design value, and blue one is a power consumption on each block. Blue one is existed performance and power consumption data. Next slide, please. What is the important point of those equipment while we are selecting the whole entire processes? So the intake is very important because eventually we are producing food grade salt and we are using lots of membrane system, and we need to eliminate and prevent TDS fluctuation. If you consider the monsoon season and very huge rain season in Indonesia, the seawater TDS fluctuating a lot, which is around 20 to 15%. So if you consider those fluctuations, and if you also consider to produce constant salt amount at the end, our plant has to be designed based on 20% bigger in order to eliminate fluctuation. Instead of this, and we built deep intake piping into the ocean, and also it's helped us eliminate contamination and also organic loads of the plants. And ultrafiltration, when we select the high recovery ultrafiltration membrane system, and of course we focus to low STI, which is tight UF membrane, not like a weak UF membrane. We focus less than 100,000 Daltons, the ultrafiltration membrane, because it should be also reduce a little bit TOC. And the nanofiltration, as I explained a little bit previous flights, the membrane, which is we select on nanofiltration, has to be lower rejection for sodium chloride and higher rejection as much as possible, of course, calcium, magnesium, and sulfates. And of course, it's helping to us eliminate heavy metals and organics, and also those contaminants will not able to pass into the salt. The seawater, it's a regular seawater, and it's working under the nanofiltration permeate brine, and it's almost pure sodium chloride solution. There is a little bit contaminant, calcium and magnesium, in terms of, and of course, sulfates. That's why there's no challenge on this membrane, and it will be run at least more than replacement rate will be more than 8 years. And of course, we look into that direction, which is high recovery. If you consider the high recovery of the reverse osmosis, and we do design 2 stages, which is unusual for regular seawater RO plants, and it's running under the 75 to 77 bar. If you consider this pressure and 2 stage, and also internal concentration polarization, the compaction is getting very important points for membrane. So that's why we select different kind of 2 membrane. We are using very tight membrane on the first stage, and we are using a little bit loose membrane on the second stage in order to eliminate flux distribution problems. And of course, we select the low fouling membrane. And next one is osmotic last reverse osmosis. This is our expertise area, and we do have some patented processes, and we engage with Toyobo a long time, and we produce specially modified the brine concentration membrane, and we use this membrane in that project. And this membrane has a low fouling, low compaction, and this membrane is a hollow fiber membrane, and is not a flat sheet membrane, and each diameter, I believe the Masumoto will give you more information about membrane spec. That's why I'm going to pass a little bit fast on that section. But material is cellulose acetate, and each membrane surface area around 1,000 square meter, and it's also providing us lower power consumption and higher replacement rates than regular the other membranes. And crystallizer, this high-grade material selection was the important point of the design, because we are producing food-grade salt. The body was monel, body is monel, and the fouling film operator is La31. And there is one of the important point was the particle size and salt purity. as well as the high recovery of NS. And in addition to this, the energy efficiency was a very important point for crystallizer. Next slide, please. Key performance that I would like to give you some brief information about this. The overall water recovery is 80% of the 80%, and we are producing 220 ton to 220 ton 1,000 ton per year food grade salt. And our desalinated water production is 21 plus. If you consider condensated water, it will be around 24 to 25,000 cubic meters per day. Specific power consumption, energy consumption, including thermal section, around 9.55 kilowatt hour per cubic meter water. And excluding thermal, our power consumption, especially for this case, because in this case, which we have right now, the higher TDS feed case, because of right now we are summer season in Indonesia, 5.38 kilowatt hour by cubic meter water. And of course, this is also very important for us because this is the one of the operational costs for entire system. 375 kilowatt hour per ton kilowatt hour energy that we are spending for salt. That's also critical for us, and total power consumption is 9.6 megawatt hour by hour. Next slide, please. This is the plant layout. We do have pretreatment and brine concentration section, as you can see, and crystallizer, as well as balance of plants. This is just simple layouts that we can share with you. Next slide, please. And the pretreatment and seawater arrest system. As you can see on the just left side on the photo, the plant is consisting 3 identical trains in order to provide continuous production to the customer. We do have UEF modules as from Memstar and NF membrane from Suez, the ARO membrane from Suez, and the entire process is provided by the Danfoss as a high pressure pump and energy recovery devices. There's one critical point why we selected positive displacement pumps for this application. This is not regular reverse osmosis. On the regular reverse osmosis system, we are driving the system constant flux. But in our case, we are driving the system different flux because in case of the low TDS on the sea, we should produce same amount of salt at the end. So that's why the system design based on different flux. If you consider these 2 parameters, that means flow will be fluctuate and the pressure will be constant, and the regular centrifugal pumps is not addressing to your requirements if you consider high efficiency. Next slide, please. And this is our hearts of the plant, the Hyrec, the membrane-based concentration system, which is name is osmotically assisted reverse osmosis. And we are providing tailor-made solution, and by combining priority OARO concentration processes with many other technologies. This case that we are looking, this is just sodium chloride and seawater case, and we are also working on the lithium chloride and lithium sulfate, as well as other minerals concentration processes. OARO is directly translated into the improved plant performance and reduce overall cost by means of capital and operational cost. Because we are reducing volumetric flow of the brine and concentrating the brine and reducing 4 times evaporation volumetric loads. So this is one of the biggest item that I want to mention here. Long membrane life. Minimum 6 years we used our financial models. And until now that we spent more than 1 year and we haven't seen any degradation, any performance loss on the membrane. So, and at least according to our investigation and according to today's experience, we will see more than 6 years replacement rate. And I just want to explain about what is the differences and what is the point of to change the membrane, regular reverse osmosis membrane. What I mean by that, and when we look into the reverse osmosis membrane performance, if the salt passage is getting lower, sorry, and that means the permit TDS and desalinated water TDS is getting higher, and also differential pressure is getting high on the membrane, we are considering that, okay, we have to start to change the membrane. But in our case, the salt passage increases, meaning that to increase the performance of the membrane, which is we are not caring of this performance reducing on the membrane. That means the membrane life will be longer than regular RO membranes. So as of now, we are considering minimum 6 years, but we will see more than 6 years. Next slide, please. And this is some pictures from the existed plant, and the feed concentration is 8%, and outlet concentration is 184,000 milligram per liter, and the feed flow is 606 cubic meter per hour, and we do use 1,080 pieces the osmotic assisted RO membrane from Toyobo, and we do have 6 pieces APP 678 high pressure pump from Danfoss. And we do have 6 pieces ISEV 50 from Danfoss. This is the 2 critical equipment for us, and our pressure fluctuation also very high, because depend of the membrane performance, pressure requirement will be increased on the constant feed flow. If we consider these 2 parameters, we do need, of course, high efficiency. We do need positive displacement pump with long term life. So that's why we selected these products from Danfoss. And also, this is one of the critical points, which is we never seen commercially performed these energy recovery devices into the any kind of osmotically assisted RO processes. So that was one of the challenge, but Danfoss product was completely suited with this application. And also, if you consider this TDS level, which is ultra critical concentration, you don't have really very flexibility on the markets, because this is unknown point, not just for pump, but also instrumentation, pressure vessel, piping, and material, and all will be very complicated on that side, because that place over than 100,000 milligram per liter. This is that area for whole market. And we do have a 1,080 pieces pressure vessel from Protec Arisawa, and those equipment has been running more than 1 year. We never seen any problem, any reducing performance, or any degradation, or any problem on those equipments. Next slide, please. And this is another picture that you can see here, also concentration on the instrumentation. That's just for information. Next slide, please. And I just want to give you a little bit introduction about membrane replacements. And we do expect 10 years for ultrafiltration membrane, and 3 years for nanofiltration membrane, and 6 years for seawater RO membrane, and 6 years for osmotic acid RO membranes. And those are the expected on the financial calculation. As you know, that the membrane replacement is consisting 10 to 20% of the overall operational cost. Those items is very, very critical inputs for your investigation. That's why you mentioned those information here. Next slide, please. And this is the crystallizer section that I just want to give you some idea how does it looks like. And on the right side from the construction period, this is quite big and quite heavy equipment. Also, that will be a clear picture for you to understand what is our really impact into the size, and what does it means to reduce volumetric load of the evaporation system. And overall recovery, volumetric recovery, is around 96%, because we are eliminating all multivalent ions on NF. So that's why this is quite high recovery processes. Specific power consumption, energy consumption is 36-37 kWh by cubic meter water, and all the material is special alloys and monoel titanium grade 3, alloy 22, and others. Next slide, please. And there's some pictures how does it look like for a salt packaging area. We do have 50 and 150 kg bag with semi-automatic bagging station and 1,000 kilogram bags. This is also semi-automatic bagging station for depend of the customer needs, and we do have almost 2,000 ton salt storage as a capacity. Next slide, please. Advantage, I just try to hear some brief information. I just take already long time, so I'm going to just pass this section. I will just mention some critical point here. Reduce the capital cost 40% and operational cost 75%. Those are the very critical points for your consideration. And I just want to also give you a little bit more information about IRR. Of course, it depends on the location and electricity price, water price, and salt price, but generally, we do have in that plan 28% as a investment return. And also, we are considering right now to produce other minerals from nanofiltration reject as a magnesium hydroxide. And we are also, we already considered and invested to produce potassium chloride and bromine from crystallized reject. But next, we'll be considering the magnesium hydroxide production from nanofiltration reject. Next slide, please. And those are the chemical consumption. Those are the regular chemicals in the market, and most of them on the crystallizer section. And also that will be a great idea for you if we reduce its hydraulic load. What will be the impact into the chemical consumption? Its load around from on the operational cost as a percentage, the chemical consumption cost will be 2 to 5% of the overall operational cost. Next slide, please. And there's some challenge that we want to mention here, and you should also consider those items. And transportation difficulty is actually was one of the biggest item. We do plan to transport the entire equipment from Europe to site via sea and as well as from by lands, but it wasn't possible to transport in Indonesia. So that's why we built another place in the seashore. So just to install, and they installed to the sites. So those are the challenge that we saw in our experiences. And also long construction period for crystallizer. Thank you very much. I took already a long time. Thank you very much to all. I will be answering the question Q&A. So thank you.
Thank you, Mr. Ozdemir, for your information. I've noted there are already some questions. So if people have questions, please place them in the Q&A section. And then at the end of the webinar, the presentation will go through the questions. So now I would like to introduce the second speaker. And the second speaker is Mr. Georg Herborg of Danfoss. He's the Director of Innovation. Mr. Herborg holds a PhD in physics from the University of Aarhus, specialized in atomic scale studies of metal oxide surfaces. Since 2017, he has been the Director of Innovation at Danfoss High Pressure Pumps. His department oversees R&D, new product development, and the technical ownership of the current product portfolio. They also manage the internal laboratory at Danfoss, where all products and prototypes are tested and validated. So let me introduce you, Mr. Herborg, as the second speaker.
Thank you very much. And thank you to everyone who signed up and dialed in to our webinar here today. And thank you to my partners here presenting with me on today's webinar on the Maven salt production side. I come from company Danfoss, and if you pick the next slide, Jantje, Danfoss is a company that is having many different types of products and technologies in the total group portfolio. It's a large global company, 40,000 plus employees, located in basically every country in the world, more or less. And we in high pressure pumps is then one business unit inside that large global company. We specialize in water hydraulic equipment, high pressure pumps and ERDs, as Ersan has already mentioned in his part of the presentation, primarily for desalination applications, now also in these brine mining types of applications, salt production systems. We also have pumps and ERDs for wastewater, water reuse, and industrial water applications. So basically, we are a water hydraulics company focusing on pumps and pressure exchangers that are unique in the market, as we will see in the next slides I will share here. Energy efficiency is one of our primary value proposition, compactness and similar features of our products. We have been around for quite some years now, and therefore our different products and solutions are not only installed, of course, at the Maven site in Indonesia, but in many desalination plants and other systems around the world. Next slide, please. So, and I think you will see this throughout the remainder of this webinar, some of the pictures, some of the numbers, some of the values will come back. I don't think that is any harm in that. They are really strong performing values, and they shows how the brine mining concept has really been brought into a commercial viable scale here with this Maven project in Indonesia. But the saltwater RO systems, we've seen them, the numbers before, even with really high recovery rates, close to 60, very high membrane pressures, to achieve these high recovery rates out of the RO system, we still have very acceptable, very competitive kilowatt hours per cubic meter, this specific energy consumption value of 2.4. Many people also in the webinar here today have probably noticed the world records floating around, being presented, being highlighted, being promoted in the recent months of going below the 2 kilowatt hour per cubic meter mark. But this is again for desalination systems that is meant for producing fresh water at the lowest possible energy cost. As Ersan described, this is not the intention of the Maven project here. It's about producing salt, which is why the recovery rates of the RO system is very high, which is why the membrane pressure is very high, but still we are having very, very high performance specific energy consumptions here. And as was also presented, the actual piston pumps are one of the key components of delivering the energy into these up concentration steps. Our core technology is the actual piston pump, as you see on the screen here, with a cut open picture of it. It's very compact. It's very high efficiency, even if you just go to the next slide, please. Even if you change the operating conditions, as Ersan mentioned, is one of the requirements for this system, because the intake water salinity changes over time, and you're not interested in producing constant freshwater production. You're interested in being very predictable in your salt production, which means that you have to vary your operating parameters, and choosing actual piston pumps for those types of applications benefits from the constant, very high energy efficiency that these types of products have, even when flow rates change, even when pressure values change. We will see that a little bit later as well. Then you build up capacity by installing them in parallel. There was 3 trains in the seawater RO system, each with 4 pumps in parallel to give you the total flow rate required for each train. They are easy to maintain also on site. Spare parts and other types of tools needed to do the service is easy to keep there on site, and service crew members can easily be trained to perform whatever service is needed there. You don't need to ship these halfway around the world for specialists to take care of them. You can do that yourself. Next slide, please. And then we have the energy recovery devices. Again, many of you here in the webinar are from the desal or related industries, so isobaric pressure exchangers will probably not be new to any of you. But the energy recovery device from Danfoss has an additional feature in the way that we are combining the isobaric pressure exchange principle with the booster pump that is required to drive the flow around in the high pressure loop, whether it's in the OARO stage or it's in the seawater RO stage. You are here having the opportunity to build a single unit with a pressure exchanger and a booster pump all combined into one. That gives you some benefits. It gives you compactness. It gives you a simpler installation. You don't need to connect your pressure exchangers and your booster pumps with pipes and fittings and clamps and whatnot. They are built together into one unit. And then just like the actual piston pumps, these isobaric pressure exchangers and booster pump combined ERDs, they allow you to very nicely and very precisely to control the flow rates through them. Just like on the actual piston pumps, the flow rate through the pressure exchanger is then controlled completely by the rotation speed of the unit. So you don't need to measure your flow rate. You can simply calculate it by the rotation speed of the electric motor driving the booster pump. And this saves you, again, some connections. It saves you some CapEx equipment, and it gives you a much simpler and easy to manage total system design and layout. Just like with the actual piston pumps, you put them in parallel if you want to build up higher capacities. For the seawater RO stage, we have 4 in parallel, and they work independently of each other. You can drive them in parallel with the same settings, and you can also vary them if you should have a desire to do so. So these are the actual piston pump technology and the isobaric plus built-in booster pump technology that we in Danfoss call iSafe. That's the brand name for us. And in the next few slides, we will see how they're then built into these 2 different concentration steps of the Maven plant. Next slide, please. So here again, the system layout that Ersan also showed earlier. We have the ultrafiltration step from the left as the first one, nanofiltration as the second one, the seawater RO stage, the osmotic assisted RO stage, then coming before the high concentrated brine goes into the evaporator and the crystallizer. And you've seen the specific energy consumptions for the process steps boxed into the red one and the total system one boxed into the green dashed box here also previously. And now we will sort of take a step into these 2 process steps, the seawater RO and the OARO step, where the Danfoss products are being put to use. Next slide, please. So classic seawater RO diagram design, high pressure pump delivering whatever pressure you desire to have on the high pressure side of your RO membrane. We have the brine reject coming out from the membrane, getting pressure exchanged and boosted inside the iSafes, and then feeding back into the feed side of the RO membrane. And this is exactly what I tried to explain previously, that you don't have what you normally find in these kind of diagrams, the additional high pressure booster pump and the additional high pressure flow meter sitting after the ERD step in the RO diagram here, because it's all built into the iSafe. The flow control from the rotation speed allows you to throw away the high pressure flow meter and simply calculated by the rotation speed of the electric motor. And the booster pump is built into the iSafe from the beginning. So it's a nice and compact and easy to operate from a process perspective for the RO stage here. And it's running at relatively high pressures, 71 bar on the high pressure side, very high recovery rates, which of course then gives you the up-concentrated brine to take into the OARO step next in the diagram. One thing to notice here is that the energy efficiencies of the units that are built into the system, which is what allows us to get to the very, very interesting and attractive from an OpEx perspective, specific energy consumptions. The 4 APP86 sitting in parallel for each of the stages are performing at 91%, or here it's noted 91.6% energy efficiency, and the combined pressure exchanger and booster pump in the iSafes are also well into the 90s, 93.5% here. And these are values that you keep even when pressures and flow rates change in the different flow channels of the seawater RO system that you sometimes need to do if your feed water quality or feed water composition changes. Next slide, please. So the seawater RO step, 4 pumps in parallel, 4 iSafes in parallel, 3 trains all together, which makes a total of 12 units of each. For the RO stage of the Maven project, it's modular. You can have flexible operation of your system because you have 4 different pumps to adjust the flow rates through. You have super high energy efficiencies even when flow conditions change, and I've tried to illustrate that in the graph in the bottom left, where you see measured efficiencies of the iSafes in this case with varying flow rates through the high pressure side of the pressure exchanger unit. So you really keep high efficiencies as you tweak your operating conditions to give, as Ersan also mentioned previously, constant salt production out of your total system. And then the last thing to mention here is that because you are having 4 individual pumps standing in parallel, you are able to that builds up the total capacity that you need. You can use standard low voltage electric motors to power these units, which gives you a much more manageable and a cheap installation price. The table to the top right shows just one slide back, please. Can you hear me? Can you go one slide back, please? Yeah, the table to the top right just shows how the different efficiencies are kept well over 90, over 91 for the APPs and over 93 for the iSafes, even when flow and pressure values change by a considerable amount. Next slide, please. And now we're stepping into the OARO part of the up concentration step. So again, zooming into that orange box in the next slide. We see the basic parameters, and we see a picture of 2 of these pumps sitting in parallel for this process step. Very, very high concentration levels, especially on the outlet of the OARO step here. We have 3 trains again with 2 pumps and 2 iSafes installed in both of them. Next slide. And this is what the diagram looks like. If you take 2 steps back and keep one eye closed, it kind of looks like an RO system almost. The pumps and the ERDs are performing very much the same functionality. It's pressurizing the up concentration from the brine reject from the RO stage, and the iSafe is making sure that you have very high energy efficiency as you circulate your your up concentration fluid on the high pressure side of your hollow fiber membranes here. One thing to mention, especially when you go into these very, very high concentration levels, above 100,000 milligrams per liter, all of the products, the actual piston pumps and the eye saves used for this project are made from machined forced bar material. And that means that you are able to use a supremely high quality of super duplex for these machines that you put into these very, very corrosive environments. When you produce your machine components from forged material, you are able to achieve a much higher corrosion resistance and really have a supreme quality compared to if you were, for instance, producing your casings or your housings from a casting process. So because these actual piston pumps and these eye saves are made from bar, machined, whether it's the house or it's the connectors or it's the vane pump or it's the pistons or it's the flanges, whatever, it all comes from really high grade quality super duplex material. And that also means that we are seeing very, very good corrosion resistant performance even at these aggressive operating conditions with salt concentrations close to 200,000 milligrams per liter. Next slide. And here, just like before, you see a summary of the benefits. We've been through them, the high reliability, even with very high salt concentrations. And again, here on the previous slide, it was the iSafe energy efficiency I showed in the graph. Here I show the actual piston pump total efficiency when the flow requirements vary from 106 point something to 109 cubic meters and a half, you still have 91% or better energy efficiency of your pumping station. And in the table to the top right, you see the same performance as before. Flow and pressure might vary, but your efficiencies, they stay high. Next slide, please. So a summary of what I've tried to share with you all here today. Actual piston pump and iSafe energy recovery device technology is giving you really supreme high efficiency, especially when you have these operating conditions change over the year and over the membrane degradation cycles. You want to change your flow rates, you want to change your pressure levels, but you keep your high energy efficiency levels. And then the reliability and the durability of the units that I mentioned, the forged material components, the long-term reliability of the units, and the easiness when you do have to replace something that has been worn, you can do it directly on site within a few hours in the plant, very easily, very effectively. Thank you for your time, and just like Ersan said, I will be around for the Q&A session at the end.
Thank you, Mr. Herborg, for your presentation. Now I would like to introduce Mr. Nobuyuki Masumoto. He's currently the Chief Technical Officer at the Arabian-Japanese Membrane Company, where he leads the membrane business development and sales in the MENA region. And he focuses on functional membrane products based on the Toyobo MC technology. So prior to now, so between 2008 and 2018, he worked in membrane development and sales at Toyobo. Mr. Masumoto holds a bachelor degree from Shinshu University in Japan. Please go ahead, Mr. Masumoto.
Hi, everyone. So my name is Nobuyuki Masumoto from Toyobo MC. First of all, I'd like to thank all of the organizer, IDRA, the host, the Danfoss, and our best partner, Hyrec, to give me this kind of a great opportunity. So today, I'd like to introduce the Toyobo MC's membrane business and the brine concentration membrane technologies. And just for your information, from this April, I just transferred the company from AGMC to Toyobo MC, and now I'm working in Toyobo MC as a leader of the brine concentration and forward osmosis membrane technology. So let me go to the first about the Toyobo MC Corporation. So next, please. So we are Toyobo MC Corporation, who is just established last year by Toyobo and Mitsubishi Corporation, who is a well-known Japanese company. And 1/3 of business and technology has been transferred from Toyobo to Toyobo MC Corporations. Next, please. So this is just our company business profile. So it's too detailed, and due to the time constraints, so let me skip this page, please. Next, please. So this is the Toyobo MC business, the product lineup, and mainly we have the mainly resin and chemical product and environmental and fiber product. So next, please. So this is just an example. As for the resin and chemical products, we do have the plastic materials mainly used for the car parts, and also some fine chemicals for pharmaceutical and agrochemicals. Next, please. As for environment and fiber product, we are serving the VOC treatment equipment, the cushioning materials, non-woven fibers for the air filtration and sanitizations. And also we do serve the water treatment membrane product as well. Next, please. So next, I'd like to show you Toyobo MC membrane lineup. As of today, we are expanding the membrane business field, and we are serving so many multiple various type of functional membranes, such as reverse osmosis hollow fiber membrane, spiral wound RO membrane, forward osmosis membrane, brine concentration membrane, MBR, and so on. Next, please. So the most unique membrane in our product is the hollow fiber type membranes, which consists of the cellulose triacetate as a raw material. And as you can see here on the pictures, this is very unique, and the million of hollow fiber are wound into the one module construction by a very unique cross-binding techniques. Next, please. So thanks to this very unique membrane configuration and the unique raw materials, that we can enlarge the surface area around 10 times higher than other membrane type, which is realizing the greater dilution of the fouling load. And also the CTA chemistry offers superior chlorine tolerance, which means we can effectively reduce the operation cost, especially biofouling control, by direct chlorine injections. Next, please. So from the next slide, I'd like to focus on brine concentration membrane. So based on our hollow fiber CTA membrane technology, which is our business foundation, currently we are expanding the membrane applications, not only the RO, but also the forward osmosis, pressure retarded osmosis for the electric power generation, and also the osmotically assisted RO, which can be utilized for the brine concentration systems. Next, please. So Toyobo MC-BC membrane is commercially proven and applicable for wider range of the industries, which is requiring brine concentration and zero liquid discharge. Next, please. So this is our brine concentration membrane module configuration. Actually, our brine concentration membrane configuration is quite similar with our normal reverse osmosis hollow fiber type RO membrane configuration. That means, so we can easily produce this OARO brine concentration membrane using our current available production asset. And if we look at the product specification, which is also quite similar to our OARO membranes. So we are using the cellulose triacetate as a raw material, and we can still keep the very high membrane surface area around 600 meter cube. Next, please. So this slide is showing the up concentration technology landscape, total dissolved solid versus energy usage. So this slide is already explained very well by Ersan. Therefore, I'd like to skip this slide. Please go to the next. So let me briefly explain what is the OARO, how we can utilize this OARO technology. On the left-hand side, you can see the RO mechanism. So everybody knows the RO mechanism. Once we will introduce the one solution to the feed side, so we can get a high concentrated water and permeate water accordingly. OARO case, since our OARO membrane has a unique module characteristics, we have 2 inlet port and 2 outlet port. So we can introduce the same concentrate solution to the 2 inlet port. So which means the flow fiber outer side and flow fiber inner side, we can introduce same concentrated solution, which means we can cancel the osmotic pressure difference between the 2 sides. Therefore, once you will apply the pressure, from shell side to bore side, water molecule can easily move. And at the end, we can get more high concentrated water, and we can get more diluted water at the outlet side. Next slide, please. Using this very unique mechanism, we can maximize the concentration level more than 200,000 milligrams per liter by multi-stage OARO system configurations. But this is an OARO multi-stage configuration system method. Please go to next. So thanks to the unique OARO system configuration as well as the Toyobo MC-BC membrane characteristic, we can realize very effective low energy consumption compared to the other membrane BC technology as well as a conventional thermal technologies. Next slide, please. Okay, from the next slide, I'd like to focus on the Maven salt production project. As Ersan and Georg already explained about the Maven project, this is world first OARO commercial salt production plant. And below table is showing the overall system configuration. And if we look at the OARO system part, the Toyobo MC-BC membrane has been selected thanks to the great decision by Hyrec. Next slide, please. So let me elaborate more about OARO system design. So actually the OARO system configuration consists of the 4 stages per train by 3 trains. And the membrane number is allocated accordingly like that. And a membrane has been selected Toyobo MC membrane, the FP10 models. And this is the kind of the DCS screenshot at the initial stage, initial operation period. And the OARO operating pressure is around 54 bars at the initial stage, initial period, and the concentration level at the final stage was the 178 grams per liter as per the design. Next slide, please. Let me show you more detail about the OARO membrane performance. So this slide is showing the flow rate volume parameters for the first stage shell inlet flow as a blue color, and the 4th stage shell outlet flow as a gray color, and the final concentrated flow volume as orange color. So as you can see here, the flow rate volume has been quite stable during the whole period as per the design, thanks to the great operation and maintenance control by Hyrec supervision. Next slide, please. So in this slide, I'd like to explain more about OARO performance operational parameters. Above graph is showing the shell side operating pressure at first stage inlet and fourth stage outlet. I'd like to highlight that during the initial 20,000 hours period, the operating pressure has been quite stable around 60 bar, and between the first stage and the fourth stage, pressure drop can be minimized accordingly. And below slide is showing the salt maintenance ratio, which means how BC membrane can eliminate salt leakage from shell side to the bore side. As you can see here, that we can maintain 100% maintenance, which means mechanical leakage never happen. So we can very sufficiently, efficiently concentrate salt. Next, please. So this graphic shows the salt concentration level at each stages on the shell side and bore side accordingly. So as you can see here, the salt concentration level at each stage is well satisfied with the design condition with a high stableness. So inlet concentration level is 80,000 and the final concentration level is 180,000 and quite stable trend. Go to the next slide. So next, please. So thanks to this great successful reference in the Maven project, we get more confident on OARO membrane technology, and we are now challenging and entering the new business field, not only the salt production field, but also wastewater, ZLD, lithium mining and recovery, and nutrient recovery as well. Next, please. Let me show you about our commercial refinery. Please go back one slide. Oops. So Alessandra, can you go back to this presentation slide? '67 page, please. Almost. Yeah. So the time is running, so let me rush up. So this is our commercial reference list. So as you can see here, we are now entering the various industrial field and getting the more references. So let me show you some example from the next slide. So one project in a chemical plant in Asia, which is wastewater GLD project, the retrofitting from electrical dialysis to the brine concentration membrane. Water source is sodium sulfate-rich chemical wastewater. And next slide, please. Next is the final landfill plant in Asia. This is also wastewater GLD project. So and also the next slide, please. And this is also the chemical plant in Asia, the wastewater GLD, and the water source is sodium sulfate-rich food wastewater treatment. So we are now accumulating so many commercial references using the OARO system technologies. So please go to the summary slide. Now the Toyobo MC has a various type of water treatment membrane, and our BC membrane is commercially proven and feasible for a wider range of industrial applications demanding brine concentration and ZLD. And our BC membrane is selected for Maven salt production project and has been successfully performing the required concentration as per the design, satisfying the demand. So thank you very much for your attention. That's all my presentation. So we can go to the R&D session.
Thank you, Mr. Masumoto. We have lots of questions. We will not be able to answer them all, but we will respond separately to the questions they were not able to answer during this session. Also, this webinar will be made available on the websites of IDRA, so you can always look at it later. But I have here a question that's probably will be a good one for Mr. Ozdemir. Someone has the question, they saw the crystallizer SEC is about 36 kilowatts hour per cubic meter water. But now you showed a dotted group of equipment with an overall SEC of 9.5 kilowatt per cubic meter. Does this mean your total SEC is about 45 kilowatts per hour per cubic meter of water?
So I mean, there's a several type of specific energy consumption we do specify for entire stage, and also we have specified a different stage, including thermal section and excluding thermal section. But if you consider only falling film evaporator and crystallizer, the specific consumption should be 36 kilowatt hour by cubic meter water. I hope that those answers will be suit your requirements.
Okay, yeah, the person that asked the question had some other questions too about it, but which we can, which will be answered offline. I have a question here that's for Mr. Masumoto, and the person wants to know whether you have to chlorinate the Toyobo membranes from time to time, or is it because it's, or can you do it without chlorination in this application?
Okay, for the time being, for OARO system, we are following the chlorination system similar to the RO operation. Therefore, as a standard condition, we recommend to inject the chlorination intermittently. So this is our recommendation, and it would be realizing the long-term stable operation, which I believe.
Thank you. Then I have a question for Mr. Herborg. Someone is asking, what is the expected life of your products in the OARO trade? And also, is the maintenance going to be higher of the products because of the corrosive environment?
Yeah, I saw that question come in from George there, so thank you for that. We don't expect the high corrosion environment in the OARO stage to be any limiting factor for the service intervals of the products there, because of the fact that we are using this forged material super duplex in all the components in these machines, and we haven't seen any signs of corrosion damage that should be a service life limiting factor there yet. You will, of course, nothing lasts forever, and everything wears, and these kinds of things. So there will be wear components inside the machines that needs to be replaced. But we are talking here about 2 to 3 years minimum service intervals. Some components 5 years inside the units when you take them out for maintenance and you replace them. One of the special good things about this Maven side is that because it is so very focused on producing high grade quality salt for food production, the water quality is super well controlled, and therefore the actual piston pumps and the eye safes in here will have very long service intervals, that's for sure. As for the plane values and these other things, I think I will reach out to you, George, to talk a little bit about what it is that you get out of using these forged materials, because it's not just about the plane values, it's also about the microstructure of the super duplex that you tap into when you go this route.
Thank you. You can take a few more questions, maybe two. This question, whether the salt purity, does it meet vacuum salt's specification?
Yes, actually more than vacuum salt specification. Our salt purity is more than 99.9, 99.8, depend of the purge ratio. And also it's adjustable and depend of the customer needs. Sometimes customer wants to more potassium content salt, so that's why we are reducing the purge and we are producing more potassium salts. So, but yes, technically our salt quality is almost to it with vacuum salt quality.
Thank you. A question for Mr. Masumoto. With respect to the membranes, the brine concentration membranes, so the OARO membranes. So how long can they be continuously operated at 70 bars and at 40 degrees Celsius? Is it possible to operate them like that continuously, or are there limitations?
Yeah, that is a very interesting question. So to be honest, our OARO membrane is kind of the brand new product, and like a commercial operational period is also the limited. So that's why we cannot say exactly how long we can operate. However, basically we are estimating the membrane performance based on the very severe operational condition, which is a 70 bar with the high temperature. Therefore, we are expecting to maintain the membrane performance very long time period, like a couple of years with such conditions. I hope this answer is satisfied question.
Thank you. And then a last question for George. What is the maximum flow capacity that the Danfoss HPP can reach?
Yeah, I saw a couple of questions on that coming in. I tried to answer them to some of you, but I can do it also here in the forum. So the largest actual piston pump we have in our portfolio today has a maximum capacity of 92 cubic meters per hour. And then you can multiply them up by however many pumps you want to put in parallel. But the single unit maximum capacity is 92 cubic meters per hour.
Thank you very much. So I think we will be concluding our Q&A session. If your question had not been answered, then you can expect an email communication from the panelists about your specific question. This webinar will be posted on our website, the IDRA website. And I would like to thank our speakers, Mr. Ersan Ozdemir, Mr. Georg Herborg, and Mr. Nobuyuki Masumoto, for spending the time and giving us quite a bit of inside information about the design, operation, and the specific key component aspects of the Maven project. And with respect to the IDRA, I mentioned earlier at the beginning of this session that we have our World Congress coming up in December, and I believe that there will also be a presentation of the Maven project that will also be presented at the World Congress. And this concludes us for this session for the day. Thank you very much for attending and listening.
Have a great day, everyone.
Thank you very much. Have a great day to all.
Thank you very much.